This is the third recording for mechanics. In this recording, I'm going to cover relative motion and Newton's laws. I'm also going to talk a little bit about circular motion and Newton's laws, although we'll talk about circular motion again later as well. So if you're talking about relative motion, if an object has a different reference frame than another object, you can compare their velocities and their accelerations, and you can sum velocities and accelerations, or even positions, but velocities and accelerations tend to be more common. And the way you do that is, if y'all remember the transitive property back in math, where if A is to B and B is to C, then A is to C, that sort of thing, you're basically going to do the exact same thing with your relative velocities. The velocity of B to A plus the velocity of, let's see if I can speed this up. Let's do it this way. This is a position, which is the same thing. Position of P to A is equal to the position of P to B plus the position of B to A. The key here is that this B and that B need to be in the same relationship. Or here, this is, here, let's do a boat crossing a river. It's probably the easiest way to do this. A boat crossing a river moves with a speed of 10 kilometers per hour relative to the water. So boat to the water is equal to 10. The water in the river has a uniform speed of 5 kilometers per hour due east relative to the earth. So water to the earth is going to be 5 kilometers per hour. If you want to have the velocity of the boat with respect to the earth, that would be the velocity of the boat with respect to the water plus the velocity of the water with respect to the earth. So that would be 10 plus 5, and it would be 15 kilometers. Now, that assumed that they were in the same direction. If one is north and the other is east, you need to put them in a Pythagorean theorem, or in a right triangle, and use the Pythagorean theorem to find the net velocity. If y'all have questions about that, let me know. Newton's laws is the next topic. So Newton has 3 laws of motion. The first law, I'm actually going to go to the summary here. First law, Newton's first law, is the law of inertia, which says that an object at rest will remain at rest unless acted on by a net external unbalanced force, and an object in motion will remain in motion unless acted on by a net external unbalanced force. In other words, the only thing that will cause a change of motion would be a net external force. Newton's second law says that force is equal to mass times acceleration. And Newton's third law says that for every force, there's an equal and opposite force. But remember that those forces will act on opposite objects. So the force of me on the chair is equal to the force of the chair on me. An inertial reference frame is a frame in which an object that does not interact with other objects experiences zero acceleration. Any frame moving with constant velocity relative to an inertial frame is also a frame. In other words, if we're not talking about relative motion, we can say it's an inertial reference frame. Force is the only thing that causes a change of motion. Again, here are Newton's laws. That if an object is kind of an isolated object, then the only thing that would change its motion is a net external force. Second law says F equals ma, and third, force of object 1 on object 2 is equal in magnitude in opposite direction to the force of object 2 on object 1. There's some specific forces we defined when we went through this stuff, and you do need to be able to draw a free body diagram. Some of the major forces would be weight, which is the gravitational force. Remember that weight and mass are not the same thing. Mass is the amount of matter in an object, or kind of a measure of the inertia of an object. I guess the physics definition is more that it's a measure of the inertia of an object. The more massive something is, the more inertia it has. And then weight is the force of gravity acting on that, or the acceleration of gravity times that mass. Friction is opposition to motion, but there's static friction when something is not actually moving, and there's kinetic friction when an object is moving. And kinetic friction will always be less than static friction, or the coefficient of kinetic friction will always be less than the coefficient of static friction. And let me say this, the static friction force is equal to the applied force up until the point where an applied force exceeds the maximum value of static friction. And the maximum value of static friction is the coefficient of static friction times the normal force. At that point, the object, if the maximum value of static friction is exceeded by the applied force, then an object would start moving and you would switch to kinetic friction, which is always a constant value. The net force is equal to mass times acceleration. You can have balanced forces, in which case you can have a force acting on an object and no acceleration of that object if there's an if there's a balancing force on it. These are not the same thing as Newton's third law forces. These are balanced forces acting on the same object, whereas Newton's third law said that force of object 1 on object 2 is equal to the force of object 2 on object 1. So just want to make that clear. These are not forces that obey Newton's third law, or Newton's third law forces, equal opposite forces. They are balanced forces acting on the same object. And let's see if there's anything in the next chapter about Newton's laws. Circular motion. Let's go all the way back to the beginning. Again, circular motion, the net acceleration is going to be in centripetal acceleration. That is the sum of all of the accelerations. It is not necessarily from one force. So you are riding on a Ferris wheel that is rotating with constant speed. The car in which you are riding is always maintaining its correct upward orientation and does not invert. What is the direction of the normal force on you from the seat when you are at the top of the wheel? Well, it's upward because you're pressing down on the seat, so the seat is pressing up on you. What is the direction of the net force on you when you're at the top of the wheel? Well, your acceleration will end up being toward the center of that circle, so the net force on you would be downward. That's the only thing that causes an acceleration there. Pendulum here, we've got tension, we've got the weight. This is the same thing as that ride at the fair, where the swing and you go out and like this. A portion of this tension will balance the weight of the object, and a portion of this tension will keep the object moving in a circle. And those are split up into their components there. How fast can it spin? These are just math problems. mv squared over r. The net force is mv squared over r. Banked curves. I do want y'all to be familiar with banked curves. You should be able to do those. The basics of a banked curve, you've got the free body diagram would have the weight of the object going down and the normal force going up. We're assuming there is no friction on this road. So a portion of the normal force will balance the weight of the car, and a portion of the normal force will keep the object turning in a circular path. That's why we bank curves. This is the Ferris wheel example again. If you are not moving in uniform circular motion, you need to look at the acceleration vector, and if there is a portion of that vector which is perpendicular to the velocity, then that portion of the net acceleration will change the direction of the object. And any portion of the net acceleration which is parallel to the velocity will change the speed of the object. Here, this object is speeding up and slowing down and speeding up and slowing down and speeding up and slowing down, which is why you can't use uniform circular motion exactly. But they're saying at this point, you've got tension, you've got the weight, and the velocity is entirely to the side. It looks like there's no net force on this. Up here you've got weight and you've got the tension at the top, which is less because it just doesn't need to be as strong. Determine the tangential acceleration of the sphere and the tension at the chord at any instant when the speed is v and the chord makes an angle theta. So you want here. Sum of your forces right here. The tension is going to equal, at this point you've got two forces, tension and the weight. And so T will nope, I take that back. T minus mg cosine theta will equal mv squared over r. That will be the centripetal force because it's toward the center of this circle. Tension minus mg cosine theta will result in a net acceleration toward the center of the circle. It equals mv squared over r, and from that you can find the velocity of the object. There is no such thing as centrifugal force. So this was always talking about if you were stationary. But now this next section talks about Newton's laws if you were like in a moving car, where you think you may be stationary, but your reference frame from the ground is not actually an inertial reference frame. So here the car's moving this way and you feel like you're being pushed out toward the edge of the car, but that's not really the case because in reality, your inertia wants to send you forward, and the net force on you is the side of the car ends up pushing you toward the side. Relative to the reference frame of Earth, the car seat applies a real force toward the left on the passenger, causing her to change direction along with the rest of the car. In your inertial reference frame, you kind of feel like you're experiencing a centrifugal force, which is not a thing. Okay, so the commonly heard phrase centrifugal force is described as a force pulling outward on an object moving in a circular path. If you're feeling a centrifugal force on a rotating carnival ride, what is the other object with which you are interacting? You cannot identify another object because it's a fictitious force that occurs when you are in a non-inertial reference frame. Again, it occurs when you are moving relative to the actual reference frame there. Resistive forces. Big one here was, air resistance. Resistance is negative BV, and we went through this. I want y'all to be able to go through to arrive at the calculus there. And actually, I'll write that one out again. We'll go through how to determine the terminal speed and stuff like that. Resistive force, I don't think you're going to see one proportional to V squared. So resistive forces, terminal speed, centripetal forces, and that is the end of this video. We went through 2 of the sections of mechanics.